I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
This week, what do you do if you get pregnant in space? How do antidepressants work? And how do we know how old our planet is? We're taking on the science questions you've been sending in to us. Hello, I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
So here we are up in Edinburgh, and so I have a bunch of people who are from north of the border who've kindly agreed to come on the programme and answer your questions. So let me introduce them to you. Sitting to my left is Christina McHale, who actually, it says here, researcher in extraterrestrial medicine. That sounds exciting. What does that actually involve there? You're really an ET doctor?
Yes, no. So it's about how the body adapts in space and looking after astronauts' health and things like that.
Because, of course, that's going up the agenda, isn't it? Because not just because we have an International Space Station and people setting records for the length of human habitation in space, but also the idea of us travelling to, for instance, Mars, which people are saying is going to happen within our lifetimes.
Yeah, it will happen, and we need to be prepared for that and the health effects it will have. So it's interesting.
So if you want to know about how humans adapt to life in space, or what effect it may have on you, and also what happens when things go wrong in space, perhaps, and how do we make people better, then Christina will answer those questions. Send them in now. Now, sitting next to Christina is John Underhill, who I've known for a little while because John's been on the programme a number of times in the past. John's a geologist, and actually part of his connection to me is that a friend of mine is a Greek scholar and realised that what we're calling the ancient island of Ithaca today may not be what it was once, and John has been involved in that project to try and find what the ancient Greeks called Ithaca. But this week you're here to answer questions about planet Earth.
that's right. I'm here as a geoscientist today. So although the work that we've been doing in Western Greece on the Ithaca myth and trying to bust that myth has also been rooted in geophysics and geology.
How old is Earth?
Well, it depends where you look, actually, but it's 4.5 billion years.
That's quite old then.
It is.
But how do you know that?
Well, you use a technique using isotopes for radioactive decay. There are a number of different isotopes you can use. You've probably heard of radiocarbon for young dates, for uranium-lead for older ones, and it's uranium-lead that has given us the insights. And we go to various parts of the world, particularly into the centre of continents, what are called cratonic areas, like northern Canada and Quebec and Greenland and so on. And it's the rocks that are taken there and the isotopic work that's done on those that gives you those dates.
When you say things like uranium-lead, that's because these are radioactive chemicals that with a known amount of time turn in from one chemical into another, and if you measure how much is there, you roughly know how much time must have elapsed.
That's correct. I mean, age dates are based on that radioactive decay, and it's a process where there's a specific atom or isotope, as you say, Chris, is converted into another one at a known rate. It's what's known as the half-life.
So if you want to ask John anything about geology and how Earth formed and how it's changing, tectonic plates, that kind of thing, now is your chance. Also here is Lee Cronin. Lee's the Regis Chair of Chemistry at the University of Glasgow. He has his fingers in lots of chemical pies. That's fair to say, isn't it? I've interviewed you about so many different things, batteries right through to how life got started over the years. You've worked on everything.
Well, we've only got 4 questions, Chris. I guess the origin of life is quite an important one. So we're trying to figure out how life got started and to make alien life if we can, and then use robots to make drugs. And then my latest kind of scheme is to work out if we can use chemicals to make brains.
So you should talk to Christina, because if she's an ET doctor, then the two of you, if you make alien life, that could come in handy.
Well, yeah, maybe.
Can work on that.
And if that doesn't send you mad, then, or if it does send you mad, then who's sitting next to Lee? That's Stephen Laurie, who's Chair of Psychiatry at the University of Edinburgh, can possibly put you right. So you're a psychiatrist.
I am a psychiatrist and an academic psychiatrist as well. So I see patients and I research the causes and hopefully cures of their conditions as well.
What does that actually mean? When you say research psychiatrist, what are you looking at?
Well, my particular interest is in the causes and treatments of schizophrenia. I'm head of the Department of Psychiatry in Edinburgh, so we have a lot of research going on into the causes of depression and autism and dementia are the main foci of our research endeavours these days.
It's pretty common, depression, isn't it?
Yep, 20% is the usual figure quoted for a lifetime risk of depression, and about 5% of the population worldwide is depressed at any point in time, so it's a very common condition, and anxiety is about the same.
Thank you, Stephen. Now, before we dive into the questions for everyone, for those of you at home, we have a little Guess Who quiz which is running through the programme. We're going to scatter the clues across the hour. Our first clue, this African animal is related to elephants? Now, the answer isn't elephant, okay? It's not that easy, but this African animal is related to elephants. Now, Christina, let's kick off with your first question.
Okay.
This one is for you, and it goes like this.
Is there a protocol for a space pregnancy?
Now, how about that for a provocative question? So, lots of male and female astronauts heading into space these days. What about if one of them's pregnant?
So that's a good question. So as far as I'm aware, no one has been pregnant in space. But if we're sending people to Mars in the future, it's definitely something we need to consider. I think there's two main things that would affect a pregnancy in space, and the first one's radiation, and the second one is a lower gravity environment. Radiation can affect fertility in males and females on Earth and things like CT scans, X-rays and things, and obviously they would be exposed to a lot of radiation in space, which could harm a developing fetus.
Is that because the radiation damages the DNA?
Yeah, so it can damage the DNA in the development. So if you were to send a pregnant woman to space, the radiation she was exposed to, the fetus would be exposed to the same amount.
How much radiation would she see? Because I thought the whole point of flying, say, the International Space Station at the altitude it does, about 400 kilometres, is that it's still protected within the envelope of the Earth's magnetic field, so it doesn't see that much radiation, or am I wrong?
So it's a lower amount, but it's higher than here. But especially on the way to Mars, for example, would be in deep space, and you get much more radiation. And I think I worked it out once because I'm very sad, and it would be something like the equivalent of 2,500 CT scans or something, which is a lot. Before we send people to Mars in general, and especially if they were pregnant, we would need some sort of barrier to that.
Because when Curiosity, the rover, flew to Mars, they actually used the radiation sensor aboard that to look at the dose it got during that journey. And I think the calculation was that were that a human being, it would have encountered an entire safe working load of radiation for an astronaut for their lifetime on that trip and back.
Well, interestingly, before I talk about the gravity, they did a study recently with mice sperm on the International Space Station, and they sent up frozen sperm, and then they impregnated mice eggs here on Earth, and the control was just normal sperm from Earth. And they didn't see a massive difference in the structure and the development of the fetus compared with DNA on Earth. So I think they found that the space radiation didn't affect the production of viable offspring.
Could that not, sorry to interrupt you, Christine, because it occurs to me, though, that if you do that experiment, the only embryos that are going to form are going to be from ones from sperm that haven't been compromised. Because you'll select for the healthy sperm that can still make a healthy mouse baby, compared with if you've got really messed up sperm from radiation, then they're not probably going to be as successful. So you might be counting the positives artificially. They
think that from this study that the DNA damage was decreased or repaired after fertilisation, if that makes sense. So it was encouraging that they found that actually once the sperm was fertilised that it had a sort of positive effect. But the other thing is gravity. That's a big thing. So because we can protect from radiation, we can find a way, but we know that lower gravity affects the bones and the muscles and vision and things like that. So because astronauts lose muscle mass and they lose bone density, how is a fetus going to develop in that environment? It's such an important time, obviously, to develop their bones and muscles and things. But
a fetus is floating around in amniotic fluid, the bag of watery fluid inside the mother. Does that not create a situation of almost artificial gravity anyway, or does the baby still end up sinking in there? Because it's sort of neutrally buoyant within the water, isn't it? So it floats around already.
I know what you mean, but I still think that the lower gravity might have an effect. We've never tested it in humans, so I can't say for sure, but I think that would be an issue. So if we could prevent the radiation and sort of make a gravity environment similar to Earth, we could definitely do it. But there will be babies born on Mars, and interestingly, Earth will be an alien environment to them, and they will develop to Mars gravity. So it's interesting. It's an interesting time.
We'll have to wait and see, I guess, won't we? It's a good job you're working on it, because it sounds like no one's got any answers yet.
But yeah, it's interesting.
Thank you, Christina, very much. Well, let's move on back here on Earth with our feet back on the ground. Let's look back actually about 60 million years plus to the time of the dinosaurs. John, we've had this question for you from Adam.
What timescale did the extinction of the dinosaurs happen over? Was it weeks or months or centuries?
Because, of course, we're all familiar with the idea that some enormous impactor rained in from space and did catastrophic things to the climate and so on. So is that not what happened?
Well, let's go back to when it actually happened. So the mass extinction event actually wiped out 3/4 of animal and plant species at the Cretaceous-Tertiary boundary, what's called the KT boundary.
How do you know?
Well, you look at the fossil record beforehand and immediately thereafter in the strata that are displayed, and you see the changes that occur over that. That happened around 66 million years ago, going back to the radioactive decay and dating of the Earth and so on. And it's actually marked by a tremendous concentration of an unusual mineral called iridium. We don't actually find it in the UK. So we have to look elsewhere for the actual golden bullet.
So it's like a signature. You're saying that written into the strata, which we can date, is this mineralogical
That's
fingerprint,
correct,
if you
although
like.
not present in the UK. Even recently, in the last couple of weeks, there have been good reports about North Dakota and some of the samples in that particular area.
So are you saying then that this stuff is not naturally found on Earth, therefore it came in with whatever did for the dinosaurs, because we can see it appearing at the right point in time when we know that event's likely to have happened?
So there's certainly an event, that's definitely right. And this is where we get to the nub of the issue, because we can date an impact crater. We can identify one in northern Mexico, a place called Chicxulub, and it's located beneath the Yucatan Peninsula and appears to be the smoking gun, if you like, for the iridium.
How big is the crater?
The crater is tens of kilometres across. It's caused massive instability in the continental shelf in northern Mexico.
So how big would the thing that came in have to have been to have made a crater that big?
Of that size. I mean, it's the size that you see on Moon with some of the craters there and so on. But whether it was actually the golden bullet that did for the dinosaurs is really coming back to the nub of the question that has been asked. Because there is another possibility in terms of what caused the toxic atmosphere at that time, and that is actually major eruptions, what are called the Deccan Traps in India, which occurred over a period of 66 to 65 million years ago. And one of the interesting things about this particular event is, of course, about 150 to 200,000 years after the iridium anomaly, we see a number of dinosaurs and other species staggering on beyond the iridium anomaly. And this suggests that actually there may have been a double whammy, that one, you had the meteorite impact, but moreover, the toxic atmosphere was actually being created by the volcanic debris and the like that was going up into the air. And that makes it more consistent with other mass extinction events through the rock record, which have all been tied back to large igneous provinces. So it's probably the two things together. And to answer the question, it was tens of thousands of years, not instantaneous.
Thank you very much, John. Well, let's actually move into the modern era now. And Lee, we've got this question for you, which is, how shall I put it, electrifying.
How does a battery work?
So there you go, the nub of it. How does a battery actually work?
So a battery just converts chemical energy into electrical energy. That's the kind of textbook answer, but it's a lot more interesting than that. Let's go back to the very old batteries, or lead-acid batteries, or maybe even to a lemon potato battery.
With a bit of copper and a bit of zinc.
Exactly. So you've got these metals, and what happens is those metals lose electrons when they react with the acidic contents of the lemon, and that reaction pushes out electrons that go around a circuit. Those electrons aren't lost, they go around the other side to complete the charge, and that push you get is what starts the way the batteries work. So that was, determined, and then we went into the lead acid, where the energy, if you like, comes from the solid lead. And as that lead is dissolved in the acid, as you power your lamp or whatever, when it's exhausted, there's no more lead left. But all is not lost. What you can do is reverse that process and put some electricity back in, and you literally push electrons back onto the lead ions, as we call them, and they form back the metal and go back to the electrode. So that's a really old-fashioned battery that is really reliable. In fact, literally billions of lead-acid batteries are still used today. But
why, Lee, can I not recharge some batteries? If I buy an off-the-shelf battery in a supermarket that's not dubbed rechargeable, I can't reverse that reaction. Why is that? Why am I told not to?
I used to as a kid, because you can get them to explode. And the problem is that you would have to recharge them so slowly, it would just take too long. And what I did is I just forced as much power in, and of course they expanded and they ruptured and all the acid came out. And that was rather bad, but I thought quite good fun. But if you take now a lithium battery, which also is kind of scary because lithium batteries can catch fire on aeroplanes, everyone is terrified about lithium batteries. Well, lithium metal is really, really reactive, but it has a high energy density, and that's why they're so good for our mobile phones. And so that literally the lithium metal being dissolved packs a lot of power. So we've been spending a long time dissolving that lithium in a kind of plastic bag, in a kind of membrane, to try and make sure that lithium goes back again without forming crystals that then cause the bag to expand. your listeners might have had mobile phones or computers suddenly warp out of shape. That's because the lithium battery has failed. I wouldn't advocate doing anything with that other than disposing of it correctly, because it could catch fire. And the other thing is, if you put a nail or something into a lithium battery, it will catch fire. Basically, there are lots of different developments in these batteries, and the quest is to get a much higher energy density battery, a bit like the one that would give you something like, I guess, the density of diesel.
Lee, thank you very much. Well, on to human health, again, having heard from Christina earlier now, and actually this is about mental health. We've got a question for you, Stephen, all about anxiety.
What's the difference between just being nervous and having an anxiety disorder?
So that's from Josh. Difference between anxiety disorder and just the random sort of panic we all experience before a programme like this one. Although I'm sure you were very relaxed.
I'm getting more relaxed as time goes by. So we all feel a bit nervous at times, don't we? Such as these, or with exams looming, or about other relatively common events in life. The difference between that and an anxiety state is really, in essence, the severity of the anxiety that one feels and how long it goes on for. Most anxiety states, for example, are defined by having anxiety for at least 6 months. And then also the fact that the anxiety is in itself distressful and or disabling. So that's how you would distinguish one of a whole range of different anxiety states from normal anxiety or stress. And then there's a number of different conditions. So generalized anxiety, for example, is feeling pretty much anxious all the time, as it sounds. Panic disorder, on the other hand, is having panic attacks, which are relatively discrete episodes of anxiety, which can be extremely unpleasant. People tend to feel that they are dying or having a heart attack or going to collapse in public. And then the other very common types of anxiety are the various phobias. So they affect a very large number of kids. 5 or 10% of kids will have a phobia to things like dogs or the dark or spiders. Most of those tend to go away with time, but they can persist. The other thing to say about anxiety states is that particularly the phobias are highly responsive to treatment, and panic disorder and generalized anxiety can also benefit from a number of different treatments as well.
What sort of treatment? Do you mean behavioural therapies to help talk people down so they don't go into this? Because my experience of talking to people who've had panic and anxiety attack type disorders is that they end up in this vicious cycle where they feel a bit panicky, and that makes symptoms like their heart thudding in their chest or they breathe too fast, which then makes them feel a bit faint and woozy, and then they think they're having a heart attack, so that makes them get even more panicky, and it gets worse and worse and worse, and
Exactly.
They don't know where to turn.
And you can end up in a catch-22 situation like that, absolutely. So yes, a variety of cognitive or behavioural strategies can help with anxiety. So very commonly they would include a physical component, if you like, of encouraging people with relaxation exercises, and the more that you do that, the better you get at it. And the more that you can employ a relaxation technique if you catch yourself beginning to feel anxious in that kind of situation, and it helps you avoid that kind of catch-22.
Or sort of talk yourself down, say, look, I know this is happening because I am making myself nervous. This is because I'm making more adrenaline go around in my bloodstream, and it's making the symptoms worse. And
Exactly.
So because I know that I'm doing this, if I know that's happening, it's not so scary anymore.
Correct, yeah.
And
exactly.
then you can break the cycle.
And if those kind of simple measures, if you like, don't work, then there's a range of other treatments that you can apply, including antidepressants, which are actually surprisingly effective for anxiety states that haven't responded to those kind of approaches as well.
Stephen, thanks very much.
So what we were trying to do with this paper is to demonstrate the ability to type using brain signals, anywhere between approximately 4 and approximately 8 words per minute, a factor of between 2 and 4 faster than what's been demonstrated before.
Each month, the eLife podcast talks to some of the world's best scientists. Join me, Chris Smith, as I hear about breathtaking discoveries hot off the press. Find the eLife podcast on iTunes or listen and download for free from nakedscientist.com/elife.
You're listening to The Naked Scientists. Today we've got a panel of experts who are taking on your science questions. So if there's something you've always wanted to know and you'd like to get a question into a programme like this, they happen once a month, you can send them in now. It's chris@thenakedscientist.com. You can also tweet @nakedscientists or find us on our Facebook page. With me this week are a panel of experts who are answering those questions, and they are Christina McHale, John Underhill, Stephen Laurie and Lee Cronin. On the way, we'll hear from our team how we make new molecules. Before that, though, here's the next part of our Guess Who game, which you can play along at home. We're giving you a series of clues across the programme, so you have to work out what this is based on the information that we are giving you. The first clue I said was this thing. It's not an elephant, but it is closely related to elephants. Clue 2, this animal has been clocked running at nearly 30 kilometres per hour. Christina, we've got a question from Ruby that hopefully you're not too sick of when you've heard it.
What happens if someone needs CPR in space?
So someone has a heart attack or a cardiac arrest and you need to try and resuscitate them. Very difficult, I would think, when you're weightless.
The problem with giving CPR in space the same way as we do on Earth is, of course, there's no gravity, so you'd be floating around. You could technically restrain the astronaut needing CPR and the rescuer to the ground, but that would take time. And the longer you leave it before you start CPR, the chances of survival decrease quite dramatically. There's 3 sort of ways to do it on the space station, which can be initiated immediately, and I'll go through them quite quickly. So the first one's called the handstand method, and as it sounds, the rescuer would put their feet on the ceiling of the space station and use their legs to push off it, and they'd push onto the person's chest who'd be lying on the ground. The other one is called the reverse bear hug, which again, like the name suggests, you would go behind the person needing CPR and give them sort of a hug and push in their chest. And the last one's called the Evans-Russellmann method, which involves the rescuer putting their left leg over the person's right shoulder and then their right leg under the person's left arm, so sort of wrapped around their back.
Like a scissor manoeuvre.
Yeah, and then giving them chest compressions from the front. In simulated studies during parabolic flights, which is the plane, the Vomit Comet that goes up and recreates microgravity and simulations
Have you been
on Earth.
On it?
No, I'd love to.
I would like
not
to.
Yet.
I'm not sure if I'd throw up, though. I think most people do, don't they?
At the Vomit Comet, yeah, I think that's why they call it.
Even people who are quite resilient still throw up.
In these studies, the handstand method has been proven to give the best quality compressions. However, the problem is if you're small, like I am, I probably couldn't do that because I wouldn't be able to reach the ceiling. So in that case, the next best one is the Evans-Russellmann method, which only had slightly lower quality chest compressions. And the advantage of that as well is you're in a position to give ventilation.
Lee?
Couldn't anyone just make a kind of compression chest, like a
vest,
like a corset?
Yeah.
You just go on and off, on and off, on and off.
Yeah, so I've been asked that because sometimes in some scenarios on Earth we have to use those, if CPR is ongoing for a long time, because the problem with human CPR is that you can fatigue and that can affect the quality of chest compressions. But at the same time, we still need to know how to do it in a scenario where, again, if it might delay time putting this machine on or it might not be available. These things are heavy and expensive as well, and we need to bear that in mind when we're travelling to space or on Mars and things like that. The reverse bear hug method isn't great out of all of them. It was the most fatiguing, and as I said, once you get tired, the quality gets a bit worse.
Well, having had to do a lot of CPR on people in my job, my medical job, it's knackering. And it's really knackering when you're on the ground, not fighting against all the exigencies of weightlessness. I should think it's probably extremely taxing trying to do that in space.
Absolutely. So I did a study a couple of years ago, and it wasn't zero gravity, but we were simulating Mars, and it was exhausting.
Oh goodness!
Because
on Mars,
you weigh less, and as you know, to give CPR here, we rely a lot on our body weight, but because you weigh less, you've not got enough strength essentially. So yeah, it's difficult.
So it sounds like a trivial thing, but actually a really, really good question, and thank you. Really good answer as well. Thanks very much, Christina. John, you sort of dwelled on this a bit at the beginning, but I think we can delve into this a little bit more. Dee has got in touch with this question about the age of the planet.
How do we know how old the planet is?
Now, you were talking about isotope ratios and radioactivity and things. So can we, because we've already discussed some of that at the beginning, can we extrapolate this slightly to, well, how do we know how old the solar system is? How do we know when all the planets formed? Because what's our reference? What are we comparing with what?
So the answer I gave before was very much rooted in rocks on Earth and where we find them and how we age date them. But of course, there are bits of debris that come in from space. And if we could date some of that debris, we can get an age for other parts of the solar system. And so that's been done as well, using the same techniques with the radioactive decay. And that gives us older ages for the solar system of the order of 4.6, 4.7 billion years, and even older than that.
What was here in our cosmic neighbourhood before the Earth formed?
Well, mainly a lot of debris that was spinning around and starting to amalgamate. And the Earth didn't really get into the state that we know it to be in until about 4.5 billion years ago.
It's amazing to think that actually you can put a date on when we formed in this patch of what was previously empty space with a bunch of rubbish floating around.
Absolutely. And if you go to those stable interior parts of the tectonic plates, you can get those age dates from Australia, from the Baltic Shield, from the Canadian Shield.
Yeah, indeed. Thank you very much, John. Now, Lee, here's one for you from Sam, who wants to know about designing new molecules, because very often chemists and scientists, especially drug scientists who make new chemicals for treating various diseases, talk about knocking up custom molecules by design. So how does a chemist actually go about that?
Okay, there are three ways of going about it. So you should think about chemists are a bit like architects when designing, say, a house. But we're restricted by the bonds that we can use, and the bonds are how the atoms get held in a given molecule. The first one is if we know roughly what the molecule looks like, say it's an already existing drug or an antibiotic, what we can do is draw that up and then add on the other parts we want. Say we want to put an extension on to the house, as it were, we can extend on some other atoms. And what we would then do is we then draw that molecule on a computer, and then the organic chemist would then what we would call disconnect it. It would take it apart in certain ways, and there's some really good rules that we can use to then go to the laboratory and actually knock that molecule together in a flask. So you actually do reactions to join those bonds up in order and then purify each step. In the end, hey presto, you should get the molecule. That's if you know where to start. The second way I can think of is by trial and error. We just make a whole load of molecules and check what they do. Are they good electrolytes for batteries, or are they good drugs, or are they good pigments? And then go from the properties. The other way is to use a computer and to do some physics and then say, right, I want a molecule that has, say, I'm going to make an LED with this molecule, so it's going to emit light. So I'd work out what colour that would be, and then I would look at how far the electrons have to move, and then go backwards. And then the computer would literally spit out a blueprint. And the fascinating thing, this thing called inverse design, this is really at the cutting edge. Chemists are really beginning to dream molecules in the computer and then take it through this process of molecular architecture.
But you were in the news in the last year because you also made a robot that could do this and learn as it did it. So you could work out from its own mistakes and what didn't work how to make better molecules better.
Yes,
make them faster.
I was trying to be coy about selling my own stuff, but in my own lab...
I mean, I'm not just planting that, because that wasn't a planted question. I did actually read the paper that you published on this, and it seems like it would save enormous numbers of chemists enormous amounts of frustration and hair loss.
Yes.
Trying to do... go down blind endings, because of course we're only able to make these things, doesn't have those rules to make these molecules, because people have relentlessly pursued all these avenues to work out what does and doesn't work.
So that kind of trial and error method of making molecules step by step used to be done by hand, and it was kind of an artisan process. And what we've done in my lab is written a programming language that can deploy those steps as you need, a bit like how you'd write some software now. And then what we do is we version control. So the idea is that we can send code to other people to reproduce on demand.
And that means you get precisely the right conditions to get the right molecule.
Yes.
Lee, thanks very much.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
You're listening to The Naked Scientists, and I'm joined by a panel of extremely brainy people. Let me tell you who they are. They're all from Scotland, because we're up at the Edinburgh Science Festival this week. And don't forget, we also have a question for you at home. We've got a game of Guess Who, which is going on during the programme. We've told you already, these mystery creatures are cousins of elephants. They also scurry around at up to 30 kilometres per hour. Here's your third clue. At most, they weigh 500 grams, so half a kilo. What do you think they are? Now, while you're thinking about that, it's time for a little quiz for our panellists who are here. So they've been answering your questions. Now we've got some specific questions for them. We're going to put them into two teams. Team 1 is going to be Christina and John, and Team 2 will be Lee and Stephen. And basically, it's in 3 rounds, and you can confer, and we'll give you a bing or a bong, depending upon whether or not you get the answer right. And the team with the most points is going to get a prize beyond price. It's the Naked Scientist Big Brain of the Week award, is what you get if you get the answer to this. OK, so here we go. Christina and John, what does the moon smell like? I'll give you 3 choices. You can have...
I know the answer.
Oh, you know the answer. Do you want to try it? Go on then. What were you going to speculate?
First, but I think I know.
I won't hold it against you.
It'll be embarrassing if I get it wrong.
What were you going to say?
Gunpowder?
I had raw eggs, gunpowder and cheese, so I think that's a bing for you guys.
Gunpowder. Sorry.
+1 to John and Christina, off to a flying start. Right, question 2. This is for Lee and Stephen. Which fruit can give you contact dermatitis? Which fruit will give you contact dermatitis? Pomegranates, watermelons, or mangoes? What do you think?
It would be a wild guess from me, I'm afraid. Let's go with pomegranates, yeah.
I'm afraid it's not. The mango. The skin of a mango, it's got chemicals which are very similar to urushiol, I'm told, which is the same
Not
chemical.
my mangoes.
It causes.
Oh, well,
it's
yeah.
the same chemical in poison ivy that our American listeners are going to be very familiar with. Poison ivy causes the contact dermatitis that's photoactivated in the skin. So that's 0 point for you, I'm afraid, on that one.
Well,
so
we've learned something at least.
Team 1 are in the lead at the moment with 1 point. Round 2. There's plenty of opportunity to redeem yourselves, you two. Round 2. Round 2 is called It's What's Inside That Counts. OK, so Christina and John, question is, carrots help you see in the dark. Is this a science fact or science fiction?
I think it's a fiction.
I think it's a trick question.
Because of the war, they wanted people to eat carrots.
So I think it's true, but I think it's a trick question because I think it's... Should we say true? Do you want to say true?
I was going to say fiction.
Okay.
Because I thought it was during the war.
I answered the last one, so let's go with fiction. Yeah, let's do it. Because that's what I'm saying. I think it's a trick question. Yeah.
So I think it's a fiction because there were lots of carrots around. People were trying to encourage people to eat them. And to eat them, they said you'd be able to see in the dark. But in fact, I don't think the carotene gives that property.
So is it right or is it wrong? The answer
I think it's
is...
false.
D-Force, vitamin A is good for your vision in general, but it does nothing for night vision. Actually, you're quite right about the war connection. It was a myth promulgated during the war. Actually, they wanted to argue that the reason our fighter pilots were so good was nothing to do with radar, which was the reason they could see so far. It was, they said, they ate lots of carrots so they could see in the dark and see very well. Well done. 2 points so far to Team 1. Lee and Stephen, humans are the only primates with chins. Is this science fact or science fiction?
That doesn't sound true. I think there must be loads of primates with chins, i.e. lower jaws.
Yeah, I would go with that.
So that sounds false.
They're saying false. Have they got the marks? I'm afraid it's not looking good for you two today. It's not true. No, humans are the only primates, possibly the only animals with a chin. A chin's more than just the bottom bit of your face. It's also a bit where the skull protrudes out before it comes back into your lips. Now, all other primates actually have jaws that sweep away from the lips. Quite funny because our early human ancestors did not have chins. And I did an interview with a gentleman who was working in Norfolk because there were some early human ancestors that would come up and have holidays in Norfolk because Norfolk used to enjoy a Mediterranean-type climate some 750,000 years ago. And this guy described these people as quite small brains. Obviously, they'd come for the warm weather and they had no chin. And when this was broadcast in Australia, a presenter there said, see, the British aristocracy obviously goes back a lot further than we used to.
Now, Chris, I come from Suffolk and I could make some comments about people in Norfolk, but I won't.
Should we do round 3 anyway?
Yes,
we've got to give you the chance to get off rock bottom.
Can we get a bonus?
Round 3, tech yes or tech no? Does this technology actually exist, is the question we're asking. Christina and John, question for you. A toaster that prints your face on the bread you put into it. Tech yes or tech no?
How would that be possible? What do you think?
No idea.
Should we say yes because we said no last time?
I think so, and it's so outlandish that I think we should go for it.
Yeah, it sounds too bizarre to not be true.
So is it tech yes or tech no? They're going tech yes.
We are.
Yes.
Yep, there's a company and they're called Burnt Impressions and they will make a custom stencil for you so you can toast your face on slices of bread that you have at
Is
home.
that our
I'm going to
prize?
buy one of those. Yeah.
I know the file format they have for that, so I could have answered that. Not fair.
So Lee's feeling hard done by. See if you can improve on this one then, Lee. A belt that releases airbags when you fall over. Is that a tech yes or a tech no? A belt that on the unfortunate occasion you fall over
Sounds
rescues you with an airbag.
No idea, it's ludicrous.
Tech yes
Let's
or
go
tech
yes.
Is it tech yes? They're saying tech yes.
Hey.
Yes, you actually scored a point. Well done. Yes, it is a tech yes. Hip Air make a wearable belt. It detects when a person is falling over and deploys 2 airbags on each hip. The idea actually it's mainly for older people because of course falls are a serious issue for them and hip fractures cause enormous numbers of ill health and actually mortality, especially in wintertime in older people, so it's very important. So you did get a point eventually. That's absolutely brilliant, but unfortunately you didn't win. So our winners this week with the Naked Scientist, Big Brains of the Week, is John And Christina, very well done.
Thank you.
Give yourself a big round of applause. And I think Lee, as the loser, you and Stephen should give them an applause as well.
We will.
Right, on with the next question. This is a question actually for you, Stephen. It's come in from Jack, who wants to ask this.
What does it mean to be schizophrenic?
So what do we mean? The phrase is so often used, but what does it actually mean?
It really is. I'm going to start by saying what it isn't, because very often what people think it is exactly what it is not. So it is nothing to do with a split personality or having opposing views about things. I think that is a terrible misunderstanding of what it is. And what it is, schizophrenia, is basically hearing voices and or having bizarre beliefs. And beyond that, it's hearing certain types of voices and having certain types of experiences or beliefs. So classically, people with schizophrenia will hear one or more voices which gives a running commentary on their actions or may tell them to do certain things or may even repeat or sometimes anticipate their thoughts. Any of those things you can imagine would be quite kind of scary experiences. Over and above that, a lot of people with schizophrenia will have persecutory delusions, so-called paranoia, but those are diagnostically non-specific. You get them in basically any psychotic condition, including dementia or delirium. But the key beliefs that people with schizophrenia tend to have are, and they overlap with experiences, and it's sometimes very difficult for them to describe exactly what it is that they're experiencing or believing. But they have the experience that thoughts are sucked out of their head, so-called thought withdrawal, or thoughts are put into their head, thought insertion.
Yeah, I talked to a lady once who told me she was very worried that her television was tuning into her thoughts.
Exactly. So they then tend to, they have these basic experiences and then they elaborate them with beliefs to try and explain them. That's a natural thing of what the human brain stroke mind does, isn't it? So we are, to a large extent at least, kind of explaining machines. And when one has these experiences, very commonly people will attribute them to the IRA, MI5, not Brexit so far, I'm glad to say, but it is conceivable that Brexit will get incorporated into people's delusions.
So they basically have an experience that they find frightening or out of the ordinary, and then they develop a story to rationalise it for them.
Exactly
so it seems reasonable for them why this is happening.
So they may be poisoned by family, friends, neighbours, or they may be bugged by any of the
But all these things
agencies
you're saying, they're people's thoughts being tuned into by television, the IRA, that kind of thing. They're all contemporaneous, aren't they? So presumably, is schizophrenia only a 20th century phenomenon? Presumably not. There must have been people back in history who had it. So would they have invented new stories that were contemporaneous to their timeline?
Well, we don't know, I'm afraid. There are no really good accounts of schizophrenia per se from any later than about 1700 or so. The ancient Greeks and Romans, for example, they did recognise a number of different severe mental illnesses which resemble severe depression or delirium, but they don't clearly resemble schizophrenia. So it's an interesting but open question. It's basically unknowable. We can't know for sure whether schizophrenia is a relatively new condition or is a condition with a relatively different manifestation.
Can I just chuck in a quick one, though?
Yeah.
Because the other thing that's risen to prominence a lot in recent years is use of cannabis.
Yes.
And people who use that sometimes develop symptoms a bit like schizophrenia.
They do,
So
yeah.
do we now, or are we of the mindset that use of cannabis is a risk factor for getting schizophrenia, or does it produce a similar sort of symptoms that then go away when you stop using it?
Both. So cannabis is a psychotomimetic drug. It produces experiences that resemble psychosis. But if you stop smoking it, even if that occurs, the psychotic experience will dissipate or gradually disappear. If, however, you've got that kind of experience and you carry on smoking it, you've got a roughly 3 times elevated risk of getting schizophrenia from the background level of about 1% to about 3%.
John?
Yeah, have the instances increased then with social media and targeted ads? 'Cause
No.
that's like people getting into your head.
No, it's intriguing, but schizophrenia seems to have has a lifetime risk of about 1%. And interestingly enough, despite all the talk in the media about epidemics of mental health problems, for example, which are, I think, essentially falsely attributed to social media, there's no good evidence that the rates of anxiety or depression are increasing, let alone that social media are a cause of a non-existent apparent epidemic.
Thank you for that really fabulous overview, Stephen. I really appreciate that. Here's a question for you, Christina, and it's from Jim.
Have we ever done surgery in space?
Nice. So you've talked about the possibility of doing CPR. What would happen if you tried to operate on somebody?
Yeah, so this is a really hot topic at the moment for missions to Mars and things like that. So On the space station, it'd be too risky. We wouldn't do surgery in space because we have the option to evacuate and bring them back home. For example, if someone had an appendicitis, it's a great example and it's a hot topic. So we would start with antibiotics. We could use the ultrasound machine to sort of assess the severity, but ultimately we could bring them home. When it comes to Mars, we are 6 months away from Mars when Earth and Mars are at their closest. Anything could happen on the way there and anything could happen whilst you're there. So we do need surgical capability and microgravity on the way there and once we're there. The thing is, with surgery in space, fluids, obviously in microgravity, that's a danger. Bloods and body fluids floating around and contaminating the ISS. Wound healing is also slower in space, and it just we wouldn't have the same resources as we do on Earth if things went wrong. So a really interesting sort of debate about this is, should we prophylactically remove people's appendixes and gallbladders, the non-essential organs?
Surely not.
It's a really interesting debate because we have to weigh up the complications that could occur in space versus the complications of, a surgery here. But it's leaning more towards not doing it because there's ethics around it and also post-op complications. And then the probability of it even happening. And now we have antibiotics, which could obviously maybe cure it anyway. So I think they're leaning more towards not removing it. But it's an interesting debate.
The other thing that's foremost in my mind is the infection control implications of doing surgery in space. Because you chop into somebody, you're going to create this aerosol of sort of spray, if you like, of body fluids and blood. Now, when we do this in an operating theatre, gravity intervenes and it all runs off the table and onto the floor and onto the surgeon's feet, and then you can clean the shoes off and everyone's a winner. But you do that in space, everyone's going to be breathing in bits of you, aren't they?
Yeah, that's what I mentioned earlier about fluids floating around and stuff like that. So I know they are developing surgical workstations and they're having to take these things into account, like watertight vacuums and things like that. And again, your immune system sort of dwindles a little bit in space as well. So there's so many things to consider, but ultimately the answer is yes, we need to be prepared for surgery in space.
We're going to have to go there.
Yeah. Which is interesting.
And one wonders, though, because you've injured yourself, I see, with your skiing exploits. Yeah, you've got your left arm in a swing.
Yeah.
What was the cause of that?
Not being very good at snowboarding is essentially the answer to that question.
Snowboarding's got a lot to answer for, hasn't it? Because the last guest we had on the programme was the Regis Professor of Botany from the University of Glasgow, and he'd broken both of his legs at Chamonix, he said.
And that's where I was as well.
Was that where you were? It must be a bad year for it.
Yeah.
But you think often treating people who've had orthopaedic type injuries is a big headache because of weight bearing, whereas in space, I suppose, there might be a benefit actually to fixing broken things because people wouldn't have to weight bear on them when they're most painful.
Well, actually, I was reading something about this, and it's hypothesised that bone healing from, say, a fracture actually might be a bit slower in space because we don't have mechanical loading and then we don't have cartilage formation. They're doing a lot of research into that as well because the bones become weaker in space, so you are most susceptible to a fracture, but actually it might not heal as well either because you don't have the weight of gravity to load and rebuild the cartilage.
So it'd be less painful but a less good healing outcome.
Yeah, exactly.
Ultimately.
Yeah.
Thanks, Christina. Well, have you guessed what our mystery thing is? We told you they're related to elephants. They run along about 30 kilometres an hour. They weigh about half a kilo. Any ideas? Anyone here got any ideas what these might be? I must admit that I'm foxed, and it's not a fox either. No one care to speculate? Dumbfounded. Lee?
Pygmy or something?
Lee's going pygmy.
No, I mean, I was thinking it was a hippopotamus or something, but then that clearly
500 grams, Stephen.
It clearly wasn't correct
Baby
when you gave us the third clue. Yeah.
Well, the answer actually is it's an elephant shrew, and it's called a senji. Senji. So congratulations if you got that right. I've never actually heard of a senji until we came to make the programme, so I've learned something from that too. Congratulations to anyone who got that right. On to planet Earth and its geology now, and we've got this question for you, John, from Annie.
How do we know what the inside of the planet is like?
Indeed. Now that's a really very good question because we're used to wandering around on the surface. How do we know what's actually going on underneath?
So one way of knowing is actually to drill into the Earth and take rock samples. And this was attempted at a place called Kola in the Baltic Shield. The drilling of a 9-inch wide borehole took place in 1989, but it only reached 12,000 metres. So
12 kilometres?
Yeah, 12 kilometres.
That's a long hole.
Yeah, 7.6 miles deep.
So how far into the crust is that, though? How thick is the crust?
So the crust is different in different places, but it can be from 10 kilometres to 100 kilometres. But they were in one of these cratonic shield areas we've been talking about before, so in the centre of one of the continents where it tends to be thickest. So they only really
So it's a good
scratch
100
the
kilometres,
surface.
so they're literally 10% of the way into it.
So that is the deepest artificial point on Earth. So we actually, to understand the composition of the Earth, of the planet, we have to rely on remote sensing. So that's using techniques like gravity, like magnetics. But by far and away, the most effective method has been seismology. And it's to use natural earthquakes that are set off on the Earth's surface or in the subsurface, and to see the way in which those sound waves that have been generated by the natural earthquakes, how they pass through the planet. And what we're looking at is variations in velocity. We're looking at how changes are recorded as that sound wave passes through the Earth. What that shows us is changes in rock properties, particularly because rocks change under temperature and under pressure. So we have seismograms all the way around the Earth to actually record earthquakes, and that allows us to build up a seismic velocity map of the internal parts of the Earth. And so we can split that out into several different pieces. Where basically we see the Earth is layered in sort of spherical shells, for want of a better word. We've got the outer part, which is the crust, as you say, Chris. That's actually less than 1% of the Earth's volume. Secondly, as we go deeper, we go into the mantle, and we have a sudden increase in seismic velocity. And then inside that, we have the core. So the centre of the Earth is the core. The mantle makes up a mass of about 2/3 of the Earth.
So that's the lion's share. I was very lucky, actually. I was in Croatia, I was in Zagreb, and I went to the lab of Mohorovčić, who was the guy who did all the amazing calculations to about 5 or 6 decimal places by hand in the 1800s to work out a lot of these sound wave propagations. He was using earthquakes to actually to do this. It was very privileged.
And that moho is actually the boundary between
exactly.
the mantle and the crust.
And they've got all these old notebooks, so it was a real privilege to see that. Now, Lee, here's a very quick one for you. We've got this question from Patrick, who says, what's the strongest acid?
Okay, quickly, it's carborane. It's a really exotic molecule. It's about 1 million times more corrosive, if you like, than sulfuric acid. And basically, acids are able to release things called protons. And this thing just likes to throw them away. 1 million times better. It's really corrosive stuff.
So what will it dissolve?
Not very much, because there's probably not enough of it.
Well, I was going to say, what do you keep it in then? Because this is a quiz question sometimes, isn't it? If you have something like that, what do you keep it in, or how do you store it? And the answer is you freeze it, because then once it's a solid, it can't be active. It has to have the particles being mobile to attack stuff.
Exactly, yeah. You want it to be a liquid.
I've never dissolved any gold. Have you ever dissolved anything gold then?
Yes, we've dissolved a lot of gold and a lot of platinum and a lot of palladium in the lab in Aqua Regia. Sometimes by accident and sometimes on purpose.
It sounds like horrible stuff, but...
it's very nasty. It's very nasty.
Thank you, Lee. Stephen, this is probably going to be the last question we have time for. We've got to finish quite soon. But what do Rob Wonder's antidepressants actually do in the brain? How do they work?
So I'll try and keep it brief. It's quite a complex question. The thing we know for absolute sure that antidepressants do quite quickly is fundamental to how they work, is they increase the amounts of chemicals that are the way that brain cells communicate with each other. So these chemicals like serotonin, adrenaline, noradrenaline, the ways that one nerve cell transfers its electric message to the next nerve cell down the line, sort of thing. We don't know for sure whether that's enough, or whether there are knock-on effects as a result of that are required for the antidepressant effect. And the sorts of things that people think are probably involved. So quite quickly, if you can show the effect of an antidepressant in people in terms of being less liable to process negative information or to process information that is neutral in a negative fashion. And around about the same time, you can also show that certain connections between different parts of the brain are enhanced. So a lot of depression is accompanied by what's called reduced connectivity between different parts of the brain that you can image with various imaging techniques.
And they sort of pep that back up towards a more what we would regard as normal.
Yeah. And I think the best way of thinking about that, of getting a handle on it, is that a lot of people who with depression are struck by brooding and very commonly worrying or obsessive kind of negative thoughts. And that's you can see that in a scanner with increased frontal connectivity or activation patterns and less long-range frontal lobe to the rest of the brain like connectivity. Antidepressants and indeed ECT, interestingly enough.
That's the electric shock
therapy. That's the electric shock treatment that is probably the most effective antidepressant and what you would have if you were very severely depressed. They both seem to work, at least in part, it seems, by reducing that frontal connectivity and increasing more long-range connectivity in the brain.
And just in 30 seconds, why is it that if you do experiments on people, you can see the effect of drug molecules, antidepressant drug molecules in the brain within days, yet it takes, say, 3 or 4 weeks before people begin to feel better? Do we know?
That's partly a myth. So antidepressants have very quick effects, and you can see clinical benefits in patients within a few days. Very often patients are the last to notice, and that's why commonly is said to take 2, 3, 4 weeks. They actually have quite quick effects within 7 to 10 days usually.
Stephen, thank you. We must leave it there. And that is in fact it for this week. We're almost out of time. It remains for me to say a very big thank you to Christina McHale, John Underhill, Stephen Laurie and Lee Cronin, who are our guests this week, and thank you very much to Adam Murphy, who put the programme together. Now, next week, we're going to be looking at cooking with a conscience. We're looking at how you can do a low-carbon cooking to cut your waste dinner, and we're testing out a brand new oven. We've got an exclusive preview of a new oven technology that the manufacturer or designer says is to do to cooking what James Dyson has done to vacuum cleaning. Till then, from me, Chris Smith, thanks for listening, and goodbye.
The Naked Scientists comes to you from Cambridge University and is sponsored by the EPSRC and Rolls-Royce.